Hello and a warm welcome to Hess's Law. There are many ways to the top of this beautiful mountain that you're about to climb. The view from the top is always the same, is an ancient Chinese proverb. Obviously they've never been up to the top of the mountains I've been to the top of. It's normally covered in cloud and you can't see a darn thing. The other funny, hilarious thing is, what is the second law of thermodynamics? Don't talk about thermodynamics. Okay, there's the fun. If you are presented with formation data, this is the thing is here. It's all about the data that you are given. You can be given formation data or combustion data or average bond enthalpy data to work out average bond enthalpy or combustion or formation. It's all about the data that you are given. If you are given formation data, the overall enthalpy of the reaction is the sum of the enthalpy of the products, take away the sum of the enthalpy of the reactants. Products minus reactants. If you're using combustion, it's the opposite way around. And this is if you're using combustion data. You got it, data. So enthalpy of the overall reaction is not products minus reactants like for formation. It's reactants minus products for combustion. Reactants minus products for combustion. If you're doing average bond enthalpy, I'm fairly middle-aged, probably even more advanced than that now. I was taught many, many years ago by a teacher who's probably no longer with us. Average bond enthalpy calculations. Bonds breaking take away bonds making. Well, you're breaking the bonds in the reactants and you're making the bonds in the products. So both average bond enthalpy and enthalpy of combustion are both the sum of the enthalpy of the reactants minus the sum of the enthalpy of the product. But formation at the moment is the odd one out, which is sum of the enthalpy of the product minus sum of the enthalpy of reactants. Those little basics that we should keep at the forefront of our mind, because what will happen is your teacher will get up and he'll show you a Hess's law cycle and he'll be very confident, and that's a wonderful thing. And they will talk about the flow of energy, and the red line and the flow of energy on the black line is equal, and Hess's law tells us that the energy difference is independent of the pathway taken. You can get to the top of the mountain if you like, from the north side, south side, or any side you want to. You could take a helicopter and jump out of it and land on the top. You've probably done some stuff at school. The top Hess's law cycle is clearly we have elements at the bottom. So that's enthalpies of formation. The definition, enthalpy of formation, formation of 1 mole of a compound from its elements in their standard states. So we have elements at the bottom going up to make reactants, going up to make products. At the bottom, we don't have elements at the bottom, we have combustion products. And this is enthalpy of combustion. Combustion of 1 mole of a compound with excess oxygen. Excess oxygen is important because if you have insufficient oxygen, you're going to get carbon and carbon monoxide and all sorts of sooty things. So we keep it clean. It's excess oxygen, CO2 and H2O. If we burn our carbon and our couple of hydrogen, we make CO2 and 2H2O. If we burn our methane, CH4, we make CO2 and 2H2O. In doing that, there is a cost, there is an energy change, and we can measure that. The unit of measure is in kilojoules, as you can see. Kilojoules per mole, sorry. A bond energy cycle, they can get quite creative, because any one of these arms, any one of these processes could be your unknown. And knowing how to interpret a Hess's law cycle is critical for success at IB chemistry. They use them a lot, as you will see in a short while in this video. By looking at these now, these are just the 3 examples. I'm not going to go through them in detail. I will do that in the second part of today's video. This is the rub, this is the point where many students just go, what did you just do? What was that? And here we've got Baby Yoda, and it's like, hungry I am, feed me you must. And then there's Baby Yoda at the end with his kind of Lord of the Rings lightsaber, whoopla, what's the whip that's going to slash him and end his life. And, you know, if people were just interested in the beginning and the end, you'd miss all the fun in between. And the fun in between, that's where chemists look. Because we know, and you'll be familiar with these diagrams, probably on the left, maybe not so much on the right, but don't worry about that. On the left, we have reactants going to make products, and that's exothermic because delta H is negative. The products have less energy than the reactants. But is that the story? I mean, on a simple terms, reactants A go into reactants B. Reactants A, what could that be? That could be flour and water and salt and a bit of yeast. And intermediate B could be baking it in the oven to make some bread, and then you add some cheese and you make a cheese sandwich. Obviously, I'm hungry. But there is a story in between how we got from our reactants to our eventual products. We can plot them on enthalpy diagrams on the right-hand side. We can see an SN1 and an SN2. If you've not done organic chemistry yet, don't worry. The whole point here is we've got Rx. R is just a molecule. It's an alkyl group, but don't worry about that. It's just a molecule. It's been attacked by a nucleophile, NUC. Nucleophile, NUC, short for nucleophile. It needs an activation energy, the minimum energy to break the bonds in the reactants. We'll make an intermediate state, and then we fall down to products. Okay, and on the right-hand side, instead of having two humps to humps to humps to humps, we have one hump. And these humps and this story, these intermediates, is what we can use to apply Hess's law to work out unknown enthalpies in an enthalpy cycle. Enthalpy of combustion data cycles. Number 1, we have ethene reacting with hydrogen, making ethane. If we call this reaction 1, here, 1, 2, and 3. We can draw our anticlockwise and our clockwise arrows, and we could say that delta H1 plus delta H2 equals delta H3, applying Hess's law. We want to know delta H1 to make delta H1 the subject of that expression. Delta H1 is therefore delta H3 minus delta H2. Delta H3 happen to be here. Those are our reactants. And delta H2 happens to be here. And these are our products. And if I had just gone in and said, well, it's the enthalpy of reactants minus the sum of the enthalpy of the products because it's combustion data, then I'd have been correct. The other way of looking at it is if we take this route from the reactants from here and we go around here, we are with the flow of this arrow, we are going in the same direction. When we hit here, we're going in the opposite direction. So while ethane has an enthalpy of combustion of minus 1561, we'd have to change the sign because we're going against it. So that becomes plus 1561. It's the same as saying minus and minus. So even within this, at this early stage, you can see there's 2 or 3 different ways to approach it. At its simplest form, enthalpy of reactants minus enthalpy of the products, you will get the correct answer, minus 118 kilojoules per mole. So there's the cycle and how the shortcut works. The shortcut still works for this one. What do we have here? We have 3 carbons and 4 hydrogens, making C3H8, which is obviously propane. And we can go around the cycle in the same way we did last time, because it's the same cycle, because it is enthalpy of combustion data. So what equals what? Well, clockwise equals anti-clockwise. Or should we just this time go and say enthalpy of reaction for combustion data is enthalpy of the reactants minus sum of the enthalpy of the products. So that's going to be minus 2326, which is here. So it's take away, well, I'll put the full lot in, take away 2219, which is the same as plus 2219. Plug that into your calculator, minus 107 kilojoules per mole. Reactants minus products, that's all good. Enthalpy of combustion data, reactants minus products. Learn it, deal with it, move on with your lives. Enthalpy of formation cycles. Here we have 3 enthalpy questions. Use standard enthalpies of formation. to determine the enthalpy of the reaction for the following reactions. Okay, how we're going to do that? Well, I've copied a data table at the bottom. Just a note of caution, all data tables are slightly different, whether using A-level or IB or AP or whatever it happens to be. They all seem to like their own peculiar way of doing these things. Anyway, what we're talking about? We're talking about enthalpy of formation. So enthalpy of the reaction for enthalpy of formation is sum of the enthalpy of the products, minus sum of the enthalpy of the reactants. So products minus reactants. Very good. So where we're going to get the enthalpies from, I'll stop scribbling on my data here. So we had NaOH, which is, where's sodium hydroxide? That's going to be here. And HCl is going to be here. So it's minus 426.7, minus 92.3. Those are my reactants. And my products are NaCl, which is here, minus 411, plus H2O, which is just underneath, minus 285.8. So I've taken my products and take away my reactants. My products were minus 411 plus minus 285.8, close bracket, take away minus 426.7 plus minus 92.3. Plug that into your calculator. Be very careful with the signs. I actually do these one step at a time. I would work out the sum of the enthalpy of the products and write that down, then do the sum of the enthalpy of the reactants and write that down. Why? Because you're going to get marks for that in your exam. So the next question, 2CO2 plus O2 goes to 2CO2. Can we get them on the screen at the same time? Maybe. Let's have a go. So products minus reactants. So we've got, let's just write that down. So we've got 2 CO2s. That's my products. Take away 2 COs, which is added to, and O2. That's products minus reactants, right? Of course it is. So let's have a look at the table. Let's go for yellow this time. So we have 2 CO2s, and CO2 is minus 393.5. Let's get used to this pen. Where's CO2? Here it is. Here's CO. Carbon dioxide is here. Minus 393.5. CO is here. Minus 110.53. And the oxygen, where's oxygen? Hey, you knew that. Oxygen is not there because it's an element, so you cannot have enthalpies of formation of an element because it's already formed. So, coming that lovely green, I'm quite liking the green today. So 2 times minus 393.5, take away 2 times minus 110.53 plus 0, we'll put it in just for completeness. And let's put that extra step in. You should get used to doing this. That's minus 787 minus a minus, so it's going to be a plus 221.06, which I make minus 565.94 kilojoules per mole. Then finally we have a combustion, which is methane with oxygen, and we're making CO2 and water. So you can just do what we did in the previous one. What are my products? My products are a CO2 and 2 H2Os. And take it away from the sum of methane and 2 oxygens. Let's put a little smiley there because we know what's going on now, don't we? CO2, carbon dioxide, is minus 393.5 plus 2 waters. Water is here, minus 241. 2 times minus 241.8. Take away methane, which is minus 74.8. plus 2 nothings. There's my smiley. Yay. Okay. So minus 393.5 plus 2 times minus 241.8 minus 74.8. I make that equal to minus 850.3 kilojoules per mole. We'll actually make that look like a 3. Jolly good. So, enthalpies of formation. Get practicing. Average bond enthalpy. Let's go. So, remember now from the previous slides that the average bond enthalpy is the sum of the breaking, take away the sum of the making. There are no reactions here, just a table. So let's make a couple up. Let's use an IB favourite, shall we? They love this one. So we've got N2, H2. It's actually an equilibrium, but that doesn't matter for these purposes. Nitrogen, hydrogen, 2NH3. A common pitfall, a common error, is people look up the wrong NN bond. It can be N single bond N, and double bond. Can it be double bond? Yes, it can. And N triple bond, which is in diatomic molecule nitrogen. Then we've got 2 lots of NH3. 2 lots of that. So it's breaking, take away, making. Well, this is what I'm breaking, and this is what, excuse me, I am making. So I'm breaking a 945 plus 3 lots of HH, which is here. 3 times 4, 3, 6. And then we've got 1, 2, 3 NH bonds, but there are 2 lots of them, so we want 6 NH. So NH is 391, so that's 6 times 391. Okay, so you can put in the next step if you want. So that's going to be 2, 2, 5, 3. Take away 2, 3, 4, 6. You could get a mark for it on the paper, just do it. And that works out at minus 93 kilojoules per mole. Breaking, take away, making. Let's do another one, just for a laugh. So let's say we're given C3, that's not helpful, is it? C3H8 plus O2 going to CO2 and H2O. Just need to balance that up. So 3 carbons, 8 hydrogens, 4 waters, 3 2s are 6, add 4 is 10, so that's 5 O2. Whenever I'm given an organic molecule, I always draw out all of the bonds. Because we're all human beings, we're all fallible, we can all make mistakes, and no one is immune to that. So I like to cross them off as I go through. So here we've got what we've got. We've got 2 carbon-carbon bonds. Carbon-carbon is going to be 3, 4, 6. So that's 2 times 3, 4, 6. And we've got 1, 2, 3, 4, 5, 6, 7, 8 CH bonds. So that's going to be 8 CH. CH is 413. 8 times 413. And we've also got 5 oxygens. And O2 is 498. 4 times 498. So that's the sum of my breaking, which I make 6486. So that's breaking. Making bonds, I've got 3 carbon dioxide, so that's 6 times 799. Don't forget CO2 is C double bond O, double bond O. So you need 3 lots of 2, so that's 6 times 799. Plus, and we've got 4 lots of water, and water is HOH. That's 8 OH bonds. So that's 8 times 463, which I make the princely total of 8498. So what should I do? 6486 take away 8498 equals minus 2012 kilojoules per mole. Breaking, take, making. Common pitfalls: not counting the bonds correctly, hence I draw them out and put a line through them. Second one is not knowing which is the correct bond between neighbouring atoms, whether it was C to C or C to O or N to N or N to O. Those are the ones. If you don't know them yet, hit the books, learn it, deal with it, move on with your lives. The final method that we can use in standard level is this. And flip multiple sum is the best words I could use to describe it. Let's have a look. Okay, we're given an equation at the top where there's ammonia with oxygen. Let's write it out. 4NH3, 5O2 goes to 4NO plus 6H2O. We're then given 1, 2, 3 equations which we need to use to solve for X. What's the enthalpy of that reaction? Well, you could make a cycle, couldn't you? Because what is giving me N2 plus O2 goes to 2NO. Well, there's 4NO. So 2NO, I need to times that by 2, don't I? So that's 2 times minus 180.5. What's the next one telling me? N2 goes to 2NH3. Now NH3, NH3 is here, but again that's 2 and I want 4. And that costs me minus 91.8, so that's 2 times minus 91.8. And then finally I've got to make 1 water is minus 241.8, but I want 6 waters. So that's going to be 6 times minus 241.8. Okay, so I can follow the arrows. So this side equals this side, and I can solve and I can say that 2 times 91.8 plus delta H, which is what we're after, delta H, so going around this side, this way, 2 times 91.8 plus delta H is going to equal our 2 times, what is it, minus 180.5 plus 6 times minus 241.8. Be careful on the rearranging. I make delta H equal to minus 1628.2 kilojoules. Okay, that's one way of doing it. What we could also do is this, and I can interrogate, because ammonia plus oxygen makes nitrogen monoxide and 6 waters. This is nitrogen and oxygen making 2NO. NO is on the right hand side here, NO is on the right hand side there, but that's 2 and that's 4, so I need to times that by 2, so it's 2 times minus 180.5. The next one, N2 plus 3H2 makes 2NH3. Well, NH3 is on the right hand side here and on the left hand side there. Not only that, that's a 2 and that's a 4, so it's times 2. And because we're going the opposite direction, if it's exothermic to minus 91.8, going from left to right, from right to left, it must be plus. So we're going to have 2 times plus 91.8. You see what we're doing? We're making this fit this equation at the top. And then finally, hydrogen, half an oxygen makes H2O. Well, that's on the right hand side. That's on the right hand side, but it's times 6. So we're going to keep the sign, we're not going to flip it. 6 times minus 241.8. And all you do is sum these up, and you'll find it's minus 1628.2. Whichever method you use, you get the same number back. We now have 3H2, 2 carbons, excuse me, half an oxygen, making 1 ethanol. Let's not use a cycle. Okay, so we've got minus 875, but this has ethanol on the left, and we want ethanol on the right. So we just flip the sign. So that's going to give me plus 875. It swapped sides, but it's the same multiple. The second one, C plus O2 makes CO2. Well, C is on the left and C is on the left, so that's good. But there's 1 C here and there are 2 there, so I need 2 times minus 394.5. And then finally, hydrogen, there are 3 here and 1 here. You're ahead of me, right? So that's 3 times minus 285.8. If you sum that up, I make that minus 771.4 kilojoules. No cycle, correct answer, passed my IB. Let's do some past paper questions.